Hi, in this part 5, we will discuss about the substitution and also the trigonometric substitution. First of all, let's make the revision for the integration by substitution. So let's say you have a problem like this. You want to differentiate this function. In this case, we look at this function is not is like a polynomial function, okay, and then for this function you power 3 over 2. So this is some sort of composite function where there are multiple functions mixed together, right? So to solve this problem, we can use the composite function rule, which is at the top here, where you have the function gx embedded inside of the function fx. So let's say we want to solve this function. First of all, you have to solve for the function f first, okay, at the outer, and then solve the inner part. So what we can do is we solve the outer part first. So for the outer part, we have a polynomial function x squared plus 3. Let's fix this. We solve the outer part, okay. So power of 3 over 2, we multiply in front after differentiation, and then 3 over 2, we have to minus 1. So this gives you 1 over 2. Then you continue, you solve the inner part, x squared plus 3. You get 2x, okay. After you differentiate x squared, you get 2x. And then the constant 3, you get 0 here. So the final answer is this term, you multiply with it. So it will be quite straightforward if you differentiate, where we can use the composite function rule to solve this problem. However, it's not so straightforward if we want to find the integration. Let's say if I give you this term, I want you to integrate on the right hand side to give me this answer. So how can I do that? So if I have a problem like this, you see this thing is very complicated, so I cannot get the answer directly. So you can see that there are many functions inside, which is a composite function, especially when you differentiate this, you get this term. So in this case, we can use the substitution to solve it. So in this case, let the t equal to x squared plus 3, and then you differentiate dt over dx, we should get 2x. Right? So we can make this substitution, t equal to x squared plus 3, and then when you dt over dx, you get equal to your 2x. So when we substitute inside this term here, we get f prime t, and then g prime x, you get dt over dx, so the dx remains here. And these two terms can be cancelled, therefore you only have this. So previously we have this term, okay, so we substitute t inside, you should get t to the power of 1 over 2 here, and then integrate. So here you cancel off, you get dt only. So therefore we are going to solve this problem, which is written here. To solve this problem, you can simply add 1 at the top, okay, sorry, so equal to t, add 1 you get 3 over 2, divided by 3 over 2. Finally, you should get equal to 2 over 3 t 3 over 2. Sorry, please take note that there's a typo here. So this will be 3 over 2, or you can write it to be 2 over 3 here. Multiply with this term. Okay, and don't forget your constant. So don't stop at this stage, because you are going to integrate the x squared plus 3 term, right? So you have to back substitute this. Initially, you let your t equal to x squared plus 3, you substitute inside, and then this will be your final answer. Right? Okay, let's check the answer here, which is the same. You should get exactly the same answer. So, problem, if you see integrand, let's say you have some function like this. So if you see this integrand fx, right, with function that has relationship in terms of gx and g prime x, means this function is a composite function. For example, if let's say I have let's say you have something like this, you see this is a composite function, you have polynomial 2x at the top, polynomial function x squared plus 2 at the bottom, so it's a composite function. So in this case, you see, if you see relationship, which means if you differentiate x squared plus 2, you get 2x at the top. So in this case, we can use substitution. So what should you substitute? So you let the t equal to this, dt dx, dt over dx, you get 2x over 2x multiplied dx. So you can use this to solve it. So let's continue with more integration, more problem for the integration by substitution. So let us continue with solving the integrate tangent x. So in this case, let us simplify the tangent x into sine over cos, where you will find that the cos function is trigonometric function, sine is also the same, it's like a composite of two trigonometric functions. So in this case, we see a relationship where you integrate, if you differentiate cos, you should get negative sign. So there's a relationship there, therefore we can say that we can try with the substitution. Like we say, let the t equal to cos x here, dt over dx, you get negative sine x. You substitute inside this formula. So first of all, for the cos x, you get t. For the sine x, you get negative dt over dx. And then dx can be cancelled. You get the negative dt at the top. So negative 1 over t. You integrate, you get negative ln t. And then this, you should do the back substitution, where your t is equal to cos x. So this will be your final answer. So in this example, we want to solve this integration where you can see a composite function for sine and cos multiplied together. So this is in power 5, power 2. So if we want to integrate or differentiate this, it's not so easy. So integration by part hardly to apply in this case. So we try to make this thing more simple, right? So in order to do this, we can always refer to the trigonometric identity, where we try to make this thing simplify. So sine 5x, let's say we separate out. Okay, this is sine x, this is sine 4x. So we are more familiar with sine 2x because we have the identity for the sine 2x plus sine to the power, cos to the power of 2x equal to 1, right? So from this identity, we can see that sine 2x is equal to 1 minus cos 2x here. And therefore, we can change this, okay, we can substitute this inside and we get this answer. In this case, let us let the t equal to cos x, because we know dt over dx, we get the negative sign. So we make the following substitution, let t equal to cos x, so dt over dx equal to negative sign, we substitute inside, then you should get this. So everything we write here. So sine x, first term is negative dt over dx, which is your sine x. So we have the first term here. Next term, 1 minus, this is our t square. Right? So we have 1 minus t square to the power of 2. So this will be our t square as well. So we multiply t square here. Then for this function, we can cancel the dx. dt we bring at the back. So negative will remain here. So these two terms can be multiplied. So for this term, 1 minus t square of 2, we expand, we should get this, right? We should be able to get this, expand it, okay, multiply as power of 2, then we should get this, 1 negative 2t square plus t to the power of 4. Then this term, we continue multiply with the t square, then you should be able to get this. So everything here you multiply with t square. Let's check. So for the first term you get t square, correct? Second term you get negative 2t to the power of 4, okay, correct? And then t to the power of 4 multiply t square, you get t to the power of 6, okay? Then we continue to integrate this. T square you get t power of 3 divided by 3. T power of 4, the constant remains. T power of 4 you get t to the power of 5 divided by 5. T to the power of 6 you get this term. So we do the back substitution, don't forget. So the back substitute, the t is cos x, we substitute inside. Then this should be your final answer. These are some additional examples that we can use the substitution to solve the integration. Where you can see for the first case, so in this case you have cos to the power of 5x here. So you can simplify it into cos to the power of 4x, cos x dx. So you can see that for this term, if you differentiate sine x, you get cos x dx, right? So in this case, we can say let the t equal to sine x, and then you differentiate it, you get the cos x. So we use this substitution to solve it. And don't forget, okay, cos x, we want to convert this into sine, you can use the identity to do that. Then for the second case, you can see that this is tangent. If you differentiate tangent, you get secant square. So that means that you can directly use this substitution to solve the problem. And tangent and secant, you should know that the relationship is in this form. Okay, always refer to your identity when you deal with function like you have a lot of trigonometric, then use the identity. Next, you have polynomial function, right, where you differentiate the bottom part, x squared you get 2x, then 2x you get 2 here. So this thing, after you differentiate, you get something like this, which has some relationship with the top, right? You can see x plus 1 term. So in this case, you can let the t to the bottom part. Okay, after we differentiate, you get the top part. So normally when you see this relationship, the answer should be in log, right? You can try it and you should get this answer. So for this composite function, it looks complicated where you have 1 minus x in the square root here. But however, you know that if you let t equal to 1 minus x, you differentiate, you get some constant, which can be, there's a relationship, okay? So we can use the substitution t equal to 1 minus x here. So if you differentiate, you should get dt over dx equal to negative 1. Also, if you have some function like square here, you can let t equal to the whole square thing. Then you can get the dt over dx equal to negative 1 over 2x. Sorry, it's a negative 1 over 2t. So let's see how if we apply these two substitutions to solve this problem. So let's start with the first substitution, which is this one. Okay, so we let the t equal to 1 over 1 minus x here, dt equal to negative dx. After we substitute, we should be able to get this form. This is the same term, so don't look at this. Let's continue with this part. So to transform this form to the next form, we can let the substitution a equal to 2 plus square root t here, this term, because when we differentiate, we get dA over dt, which is equal to the constant gone, becomes 0. So we have a term here, t to the power of 1 over 2. So this thing is t to the power of 1 over 2. If you differentiate dA over dt for this term, then we can get 1 over 2 multiplied t negative 1 over 2 at the top. So t to the power of negative 1 over 2 is 1 over square root t. Okay, so you get this form. So in this case, your dt will be equal to 2 square root t dA. And we can substitute this inside here, dt, you get 2 square root t dA. So we can write here 2 square root t dA. Well, you can see that dt is equal to a minus 2, so we can substitute inside this formula. So we get the square root t equal to a minus 2 and multiply with your dA. So the term here, we want to convert everything into a. The term at the bottom here is a. So negative 1 over a, which is this term. On the right hand side, you have 2 multiply a minus 2 dA. So we get into this form. So we multiply inside and expand the factor here. So you get answer, you get negative 2. And then this multiply here, we get 4 over a. So this is a basic form for constant. Okay, this is a basic function for rational function. So 1 over a, we know integrate it, we get ln a. So constant, we get a. And then don't forget to substitute your constant after you integrate. Then we do the back substitution. We substitute the a inside this formula. We get this form. And then we substitute again the t inside. And then we get this form. So we get back the original x. We can simplify further this formula where negative 2 multiplied inside, you get negative 4. So negative 4 is constant here. So this constant plus the constant 1, we become constant 2, which is a new constant. So we can remove this term. Negative 2 multiplied inside, you get this term, and then this remains. So this is your final answer. In this example, you can see that it's not straightforward because you may need multiple substitution to solve this problem. Let's try with the second case here. How if we let the second substitution t equal to square root 1 minus x. So this is our second substitution. After we substitute the integral, we get into this form. You have to be careful when you differentiate the dt over dx. Okay, you let the t equal to this thing, and then the square root here is equal to power of 1 over 2. So this thing I can remove in the bracket. So 1 over 2 multiply in front, you get this term 1 over 2. And then 1 over 2 minus 1, you get negative 1 over 2, which is 1 over square root 1 minus x, this term. And then don't forget differentiate the term inside 1 minus x, you get negative 1. So you have to multiply with negative 1. And the square root 1 minus x here, you can substitute with t. So you get negative 1 over 2t here. So this is your differentiation result. So with that, you multiply negative 2t to the left hand side, you get negative 2t dt, and your dx multiplied to the right side, you get dx. So we can substitute dx inside this formula, okay, and then we can let this to be t, so you get into this form. So in our left integral here, this form is called improper rational function, where you can see at the top here, the power of t is 1, and at the bottom, the power of t is 1 as well. So this can be divided. So on our left hand side, we have an improper function here, which can be further reduced. So let's try to reduce into this simplified form. We have a negative 2t at the top, and then at the bottom, you want to divide it with 2 plus t. 2 plus t here. So we have to multiply negative 2 to get negative 2t. So negative 2 multiply t, you get this. Negative 2 multiply 2, you get negative 4. Okay, so negative 2t minus with this thing, you get 0. Minus with negative 4, you get 4. So with that, this is our remainder. 4 divided by 2 plus t, which is this term. And then at the top, you have negative 2. So we are able to convert improper form to the right hand side, which is the proper form now. So let's continue to integrate this term. You integrate negative 2, you get negative 2t. Integrate 1 over 1 over t plus 2, you get ln t plus 2. And 4 constant, you remain, plus a constant. So this is your answer. And don't forget to back substitution. So let the t substitute inside, and then you should get this answer. You can see that for the same problem here, by using different substitution, we are able to get the answer. If you compare, you will get the same answer. So this method involves 2 substitutions, and this method involves 1 substitution, and you have to convert the improper function to the proper rational function. Right? So depending on which one you found it easy, then you choose the method. In this example, you should see that there are more than one method to solve a same problem, and you should master the substitution as well as how you convert the improper to proper rational function. Okay, so these two are very important techniques. So from the previous example, I can see that I can let the t equal to this square root 1 minus x, which is this one, and I found it, I just need one substitution to solve, which is much more easier for me. So for the same problem like this, I can let t equal to square root 1 minus x squared. So you differentiate dt over dx, you should get this answer. Also for this problem, we can let t equal to this whole term, which is square root 1 minus x squared. So we can get the dt over dx here. And for the x, it can be converted to t by using this formula, because from this relationship, t equal to square root 1 minus x squared, you can reverse this equation to find the x. Of course, to solve this problem, this is not the only substitution. You can let t equal to 1 minus x squared to solve it as well. Right, so I will left these two examples for you to try. How about the last example here? In this case, if you let t equal to 1 minus x squared, we don't have additional x information at outside. Or if you let t equal to square root 1 minus x squared, also the same. The normal substitution is not working here. To solve this problem, we require the trigonometric substitution, where you can see in this form is a form in the format of 1a squared plus b squared. So if you get some function like this, and if it cannot be solved by using the normal substitution, then we can use the trigo substitution.